Now we will start a new chapter, that is work, energy and power. Now first of all, going to this chapter, we learn a new method that is called scalar product. Now the question is, what is scalar product? So the scalar product, which is also known as a dot product, is a product of two vector quantities such that the resultant quantity is scalar, and their examples are work, electric and magnetic flux, power, energy, etc. So now first of all we will see that how this scalar product is defined. So to define the scalar product, we have to take two vector quantities. These two vector quantities are taken in a such manner that when they multiplied with each other, they produces resultant quantity as scalar. So now how to define it? We will learn vector product or cross product also, that is in chapter number 7, but before that, here in this chapter number 6, we need to understand the dot product or scalar product. So suppose we are having two vectors A and B. Now we are multiplying them in such a manner that they are giving us the resultant value as a scalar. So now the dot product or a scalar product is written as A dot B. It is also stated A dot B. It is read as A dot B, and when the dot product is defined, it is written as magnitude of vector A, that is mod of A, magnitude of vector B, and cos theta, where theta is angle between A and vector B. Now if we don't want to write this vector form, then we can simply say A B cos theta. So this is also the resultant term of vector product, scalar product of two vectors. So this term is called dot product of two vectors. Now here we can say that A, B and cos theta, all the three are scalars. The dot product A and B is a scalar quantity. So each vector A and B has a direction, but their scalar product does not have any direction, and therefore the quantity, that is a resultant quantity, will direction less, or not like that, that is a directionless, but it has not a certain direction that is defined by a vector product. So here the first part, that how to write and what are the basic characteristics of this scalar product has, that we will see. So first of all, how to write it? We can say that A dot B. So A dot B is equals to A B cos theta, or it can be written in a two way. One, that is A B cos theta, and it can be also written as A cos theta into B. Now here it is very important and interesting also, that what we have defined over here, the term that we have written here is a very simple thing, that we have written that a into b cos theta and a cos theta into b. Now what is the difference between these two words? So here we can explain it with one simple example, that suppose I have one vector as vector a, and suppose the other vector is defined as vector b, or vice versa. Suppose as per as if I am go with the textbook, then I can write at here this is vector a and this is vector b. Now suppose they are having angle theta in between them. Now how to term these two equations that is written above, a b cos theta and a cos theta b, different and separately? So for that, what we will do, we will take projection from the given vectors. That means if I take again, that is vector b over here and vector a like this, as I have shown above. But what is the difference now, that when I take a projection from vector b on vector a, this projected part, this portion that is covered over here, that is called b cos theta, and that is called projection of b on a. So this is nothing special, it is the same thing. If theta is the angle between vector a and b, then this is written as a dot b, it is pronounced as a dot b, that is ab cos theta. So here in bracket b cos theta term is there, so it is said that b cos theta is the projection of b onto a. So we can define it as a into projection of vector b onto vector a. So this is called first part of the definition. So the mode of a and projection of vector b onto a vector a, that is called a dot b, that is a into bracket b cos theta. Now let's see what is about the second part, that is I draw here the same figure that I will draw, little bit difference, that I say this is again vector b, I say again vector a. Now the angle is theta. Now what I will do, I will take projection from vector a onto the vector B like this. This is projection from A onto the B. So this portion I define as A cos theta. So ultimately, what is A cos theta? So here we can say that A cos theta is projection of vector A onto vector B. So here in a simple term, if I have to define it, it is like A dot B is equals to A cos theta into mod of B, and it can be stated that the magnitude of vector B and projection of vector A onto vector B. So this is the basic definition of dot product. Now there are some characteristics that it follows, so that vector product follows some of the basic law. We say it follows the commutative law, that is vector A dot B can be written as vector B dot A. I think you already have studied this, but this is the part of revision, so it is better to teach or better to revise. Now we say that it follows distributive law also. Now this is interesting, that how to divide it and show the distributive law. So here we can say that suppose this is your vector A dot, we have the summation of the remaining two vectors, say B plus vector C. Now if it follows the distributive law, we can say that it is written as A dot B plus vector A dot C. So this is the distributive law. In other way, it can also be written additionally, that is if vector A is given into dot, some multiple is given, say lambda is multiple of some value, and vector B is in some multiple value, then this term is written as lambda into the bracket A dot B. That means if some multiple is there, it will also be taken into the multiple. So this is the second law. Now one more interesting thing, that is third law that we are going to explain for unit vectors. For unit vectors, we already know that how unit vectors are given, that for x-axis we are giving I cap, for y-axis it is j cap, and for z-axis it is k cap. Similarly, for minus x-axis it is minus I, for minus y it is minus j, and for minus z-axis it is minus k. Now what? So here what we are going to say, that vector product of unit vectors like I dot I. Now we know that the magnitude of any of the unit vector, is 1. So if we are applying I dot I, this indicates that vector I dot has a value 1, another I dot also has the magnitude 1, and cos theta. But it is very clear that I cap is parallel to I cap. That means they are in the same direction, and therefore theta is 0 degree. Therefore we can say that cos theta is cos 0 is 1. So this is given by this formula, and therefore we can say that I cap into dot I cap is equals to 1 into 1 into 1. That is ultimately the answer will be 1. And in the same manner, that I dot I is equals to j dot j is equals to k dot k is equals to 1. So this will be our one result. This will be a useful result, and it is applications of this equation will be there in many examples, that we have to apply this relation, that I dot I is equals to j dot j is equals to k dot k is 1. In the same manner, if we take I dot j, then what will happen? Then again here we can say that vector I is perpendicular to vector j, and which is perpendicular to as well as vector k also. So theta will be 90 degree. Therefore cos 90 turns to be 0, and therefore in this case I dot j is equals to 0, and in the same manner we can say that j dot k or k dot I, all these will be perpendicular to each other, and that will be turns out to be 0 again. So here we can define this another rule or a law, that I dot I, j dot j and k dot k is 1, but I dot j, j dot k and k dot I is equals to 0. So this is the law. Then we move to another law. This is what that we move to the next. If we are given two vectors, say A and B, in 3 dimension. So suppose vector A is equals to AX I cap plus AY j cap plus AZ k cap, and in the same manner some another vector B is given, that is B is equals to BX I cap plus BY j cap plus BZ k cap. Then their product that we take as A dot B, and if we apply the above equations, we found that AX BX plus AY BY plus AZ BZ. So this will be the resultant answer, and this can also be written as if two vectors are same. That means if this is the result that we have obtained, then in a special case for two similar vectors we can say that vector A dot vector A, what we will get, that is AX square plus AY square plus AZ square. Now if we take them in a term of magnitude, then ultimately this would be that A as a magnitude A square as a square plus y square plus az square. So I can say as in the term that is A into A is equals to AX square plus AY square plus AZ square. Here the direction will be the same, so cos theta will be 0, cos 0 is equals to 1, and therefore we can say that A square is equals to AX square plus AY square plus AZ square, and therefore if we take only A, it will turns out to be AX square plus AY square plus AZ square. So this is also one of the important equation that we derive, that is called the magnitude of any vector, and we say that magnitude of any vector is given by this equation for the 3 dimension of the equation. This states that this is equals to A is equals to under root AX square plus AY square plus AZ square, and if two vectors are perpendicular to each other, then there will be no resultant value that we can found. So this is ultimately the explanation of scalar product, and we can also say that this chapter deals with the same type of questions. So now in the next lecture we will understand that how we can apply these laws.